Hi, so welcome to the RBR webinar. This is about RSKtools, a free toolbox for CTD post-processing and data visualization. Mark Halverson will be the presenter here. Mark, tell us a little bit about your background and your area of focus that you've been working on recently.
Oh, well, I started as a student in physics as an undergrad and also astronomy. I moved on to a PhD in astronomy, but I essentially quit it as soon as I learned that you could do physics in the ocean. And I thought, as cool as astronomy is, I mean, physics of the ocean just sounded so neat to me. So I quickly quit that PhD and moved to Vancouver and did a PhD at UBC in Vancouver. Yeah, and after that, I had a couple different research jobs, and I finished my PhD 10 years ago, and then I landed at RBR, and I've really enjoyed. I really enjoy my working with RBR. So I find the measurement side of things quite interesting, as interesting as the science itself.
Okay, thanks. And I know this is your third webinar you've given, I believe. So you're touching a lot of different topics at RBR, but how have you been specifically related to the RSKtools?
Yeah, when let's see, what's the short version of that story? Yeah, I guess when I had a short research project working with the Hackeye group, and they had asked me, this is before I worked for RBR, and they had asked me to develop a post-processing kind of pipeline for RBR data, and I learned that, in fact, that hadn't really been done or defined well yet, and so I started writing my own software to do that. And actually, shortly after that little research project, I got hired with RBR, and one of the first things I wanted to do was to RSKtools already existed, but I wanted to build it into a sort of fully functional post-processing code base, so that you could take the data, apply the kind of standard post-processing algorithms, and really improve the data quality. And so that's how I got started with RSKtools. Yeah, so I've mostly sort of directed the development of it. I didn't write a lot of the code myself. We had a number of different full-time staff working on the code base, but I helped to sort of develop the scope of it, let's say.
Excellent. And I think we should also recognize Ray Zhang, who has been instrumental in helping develop a lot of the code here and writing it and making it very usable for the customers that are using it. So Mark's giving the presentation, but Ray had a big part in doing a lot of the RSKtools portion. Finally, Mark, just before we get going, tell us one fun fact about you that the rest of the audience here would have never known unless they attended this webinar.
I'll use the same one I did last time, but I until I had kids 4 years ago, my wife and I played a lot of music together. We play a lot of old time fiddle and banjo music. So as soon as they grow up and we have a bit more time, we're definitely going to get back into the old time fiddle and banjo scene.
Awesome. Yep, that'll be good. Fun thing for them to enjoy with you. Okay, thanks. And now why don't you take it away, please? You can take it away now, Mark. You can start the presentation. Stand by. It looks like we might have lost Mark. Let me see if I can get him back online. Minor technical difficulty. Stand by one moment, please. Okay, we're working to get Mark back online. His signal dropped and should be starting momentarily. Sorry about this. Hold on, I think it'll be worth it. Okay, we've got you here, Mark. I think we heard all of your banjo. We just didn't get your presentation started.
Yep, sorry about that.
Okay. ready to go when you are.
Yeah, okay. So here we are back. I quickly realized that I was not online anymore, so I wasn't doing a lot of talking. Yes, yeah. So RSKtools. Here we go. Let's try this again. It's a free and open source toolbox maintained by RBR. It provides access to Ruskin's RSK files. So any instruments with generation 2 and later, Ruskin produces an RSK file. An RSK file is actually a SQLite database, and SQLite is a very very extremely common and widely used database. The SQLite maintainers have said they'll support it until the year 2050. So this is not an obscure data format. This is used widely on phones, and for example, on your phone, it's used widely as a database. So the RSKtools, it reads RSK files. We can do some post-processing and some visualization all within MATLAB. We're at version 3.4.1, so it's fairly mature at this point. We support 2013b and later, and we also made sure that we're not relying on paid toolboxes from MATLAB. So it just requires sort of the core basic MATLAB installation. It does not require signal processing or statistics or the image, any other kind of toolboxes. Okay, moving on. Just one slide on the sort of difference between Ruskin and RSKtools. Clearly, one is a standalone software, and the other requires MATLAB. But I mean, just in terms of the functionality, I mean, Ruskin really is for configuring, simulating, calibrating instruments, downloading data, viewing it, annotating it, and exporting it. And so RSKtools is not a replacement for Ruskin. Just to be clear about that, they have some overlap, particularly in the visualization, but it's not a replacement. And one of the most important distinctions between the two, again, is the capability of RSKtools to do post-processing, so smoothing channels or aligning channels or flagging bad data with despiking algorithms. And RSKtools, again, is a direct link between an RSK file and MATLAB. Okay, so you don't need to open an RSK file with Ruskin and then export it into another format such as Excel or a CSV text file. Okay, so we can just read the RSK file directly with RSKtools. Yeah, so the way the rest of the talk will go here is we'll talk a little bit about installing and downloading. That's pretty straightforward if you've ever worked in MATLAB before and downloaded a toolbox. Oops, yeah, let's go through that. Well, sorry, let me back up. We'll talk about the ways to get help and support, and then we'll review some of the more important functions. Downloading is quite simple. Just navigate to the rbr-global.com website, and then if you click through products, you'll find it. You can also arrive at the download through clicking support. If you move in, so that you look at software, and then in software there's a button for RSKtools that you'll get you to the RSKtools web page, and here there's a couple of words about it, current versions and so forth, and then you simply just click on the tab. Excuse me, that red rectangular button to get it. So what you'll get is a zip file. So you simply need to unzip the file and then move the folder, to where you like to keep your MATLAB functions. I just have a MATLAB home directory in my home directory, and then add the path. And there is one subfolder you may wish to add. It's not necessary, but there's something called quick start, and that's just sort of a documentation directory. So it's not required to run RSKtools, but you may wish to add it anyways. Then again, I have a lot of slides here. I could have made this a full day presentation because I like this stuff so much, but this will all be available later, right? So if I skip over something quickly, don't worry, you'll be able to get the slides later. We all of this code is version controlled, and so we also keep it in a Bitbucket repo, which is a public repo, so you don't need an account to see this one. So the link is below, and so if you like to stay on the bleeding edge, they say, as of the development, you feel free to do so here. And if you want to clone this repo and fork it and work on it and then work on this collaboratively with us, we can do the same thing. We're happy to do that. There's easily 100 functions in RSKtools, and sort of half of them are considered user-facing. There is a private directory in which has mostly sort of functions for internal use, but most of the user-facing functions have that capital RSK prefix. In general, they kind of break down into these 4 categories. These are a little bit arbitrary, but we have functions that read files. We have functions that process. So this is sort of the post-processing, smoothing and trimming data and so on and so forth, deriving different variables. We have sort of viewing and exporting, and then there's some other sort of miscellaneous things. When you need help with functions with MATLAB, RSKtools, there's a couple different ways to do it. If you're new to RSKtools, you may wish to check out these quick start demos. They're just that. They're short, sort of 3, 4, 5 page PDFs that show sort of code examples. And there's 2 of them. There's one with just sort of the basic getting started with RSKtools, how to open a file and view data for the most part. And then there's a post-processing RBR data with RSKtools as well. So that goes a little bit deeper into the algorithms and the approach you may choose to use to post-process CTD data. Those PDFs contain information that's not in this talk, so I do recommend that you check them out. We have an online documentation too. In the middle, there's an online manual. You can always type help RSKtools in MATLAB, and if you encounter bugs, then please email support@rbr-global.com. You can also file bug reports through the Bitbucket site. Either one works. Yep, so here's just a screenshot of our online documentation. So that's there. I forgot to mention this, but it's not necessary, but we do recommend that you download the TS 10 Gib Seawater Oceanographic Toolbox. I'll show you why later. And there's also the CM Ocean Toolboxes, which is color maps specific for oceanography. That's useful for one specific function that I'll talk about later on. Okay, so again, neither are required, but especially the Seawater Toolbox is very useful. Yeah, so typical stuff. You can type help RSKtools at the command window. You can type, help function name. So on the right-hand side here, you can see the documentation for the despiking algorithm or despiking function. Right, so that was getting help. So we have online sources. You can email us, and then there's documentation within the functions themselves from the MATLAB command line. So again, there are far too many functions to review. I can't review all of them in 40 minutes, but we can go through some of the more important ones. And the way I'll phrase this is through we'll do roughly sort of a step-by-step sort of CTD post-processing example as a way to introduce some of the functions. And by way of sort of kicking that off, I just want to summarize. This is kind of a big, nasty table. Of course, we're not going to go through it all here, but the first column on the left says step. So that's a post-processing step. Here I've, sort of arbitrarily broke them down into 11 steps: opening the files, visualizing it, adding metadata, calculating simple things like sea pressure and depth, filtering. And then the middle column shows you the main RSKtools functions, that will help you with that step. And on the far right-hand column, the third column, there's also other functions which you may find useful for those sorts of operations. Okay, so that's a nice little summary table you can refer to if you're developing a post-processing pipeline. Yeah, so let's get into reading the files first. The first thing you must do, this is basically the only required function, or one of two required functions to do anything, is RSK open, and that does exactly what it purports to do, which is just to open a file. And actually what it does is RSK open goes into the RSK file and it retrieves a bunch of information about the channels in the data, the profile start and end times, the serial number, the sampling rate, and some of the most basic information. It does not actually read the data just yet. And the reason we do that is because some files are huge. You could have a gigabyte of data in an RSK file. And so slurping that all in one step is not what we recommend. But this will allow you to sort of investigate the file without actually reading in a massive data set if your file is huge. And then you may move on to RSK read data. I'll talk about these in a little bit more detail again, but read data actually reads the channel data, the sensor data from the RSK file. And it reads data as a time series. So if you went out and did a bunch of profiles, you would find that when using read data, you actually read all the data as a single time series, and it's not sort of broken into profiles just yet. Again, I'm going to kind of review these again because these are the most important ones. There's another function called RSK read profiles. RSK read profiles actually looks in the RSK the structure, the data that the thing that's read into MATLAB with all the metadata, and it looks for different events, timestamps that indicate the start and end of profiles. So read profiles actually reads the data from the RSK file, but it organizes the data according to profiles. And so you can specify which profiles to download, you can specify the upcast, the downcast, or both, and so forth. So again, I'm going to go through these again. So when you do RSK open, like I said, you read a bunch of well, I guess sort of they're called tables in SQLite, but you read a bunch of different, let's say, call them fields to stay with MATLAB nomenclature. And on the right-hand side of the slide, you'll see all the different fields that exist in the structure called RSK. Okay, so the syntax here was. Let me see if I can draw a little bit. Right, so we have a structure, so it's not working. Of course. Oh, it's drawing in white. Okay, never mind. So we have an RSK structure, which is the result of using RSK open. It has many different fields in it. Most of these aren't going to be directly important for you. A lot of this is sort of bookkeeping stuff for use later on by RSKtools functions. But on the left, we've written out some important ones. Channels is particularly important. It tells you all the channels in the logger and the units that go along with it. So conductivity in millisiemens per centimeter, chlorophyll in micrograms per liter, so forth. Something about the sample rate. The profiles field has profile start and end times. Instruments has the name of the instrument and the serial number. And log is something that's quite interesting, that it actually is a running record of all the things that have been done to the data by RSKtools. So that's not a Ruskin thing. So that's RSK open. Again, most of these things you'll never ever, there's really no need ever to get into these things. But I just want to sort of open the lid to the RSK structure black box, I guess. Because it does seem a little bit cumbersome and impenetrable, but for the most part, I said you don't ever have to address these things directly. So the first thing I would do after opening a file is I would use the command RSK print channels, and this does a very simple thing, but important, which is just to print to the screen a number of important things about the file, about the data set itself, the name of the instrument, the serial number, the sampling period, the channels, and the units. Okay, so that's what RSK print channels does. It's just to kind of show you what you're working with. The next thing to do then is to read the data. So if you wish to read the data in terms of a single long time series, maybe you had a logger, a Word logger. So in which case I would use read data because there's no profiles per se. Read data is nice because it goes in. The nice thing about read data is that, you know, if you have a 1 gigabyte data set, but you don't need to read the whole thing, you can specify start and end times. And that will speed up the operation of reading the data. In T1 and T2 here are in date num and MATLAB date number format. So what happens is when you call RSK read data, so let me back up, and there's a little variable screenshot there. There's a new field called data. That's exactly what it is. Data is itself a structure that has a timestamp field and a values field. So that's literally the timestamp and MATLAB date num format and the channel measurements. And if you look at the rsk.data.values field, there you'll see literally the sensor values. And each column is a different sensor, and each row is a different sample. Okay, but it's not even that frequent that you have to actually go through and look at that level of I only rarely actually go to that because RSKtools is designed to actually act in a sort of object way. It's sort of designed to access the values field. You don't rarely have to navigate to it yourself. And then you can use that RSK print channels, or you can also look at a field called rsk.channels, and that tells you what each column is. So here you have 7 columns, and rsk.channels has 7 different fields. Okay, and each field has a name and a unit. Okay, and the sort of complement to read data is read profiles. So if you had a logger, a CTD, and you made a bunch of profiles with it, the Ruskin or the logger, one of the two, actually auto detects the profiles and then timestamps them. And so read profiles just uses those timestamps and it organizes the data according to profile. So rsk.data is now a multi-dimensional structure array. And it has each element of rsk.data is either the upcast or the downcast of a profile. You can kind of see that in the table. There's a profile number, 1, 2, 3, 4, but those profile numbers are doubled up, and that just shows you that the first element's a downcast, second element's an upcast, downcast, upcast, and it alternates back and forth. Okay, but again, you don't really, RSKtools is designed so that this is all kind of under the hood, and you don't really need to mess with that too much. I'm going to skip this one for now, but it's actually, well, the very short explanation is that if you read the data as a time series, but then want to convert it to profiles, we've made a function for that too, called time series to profiles. So this one's particularly useful if you know that the logger or Ruskin did not do a good job of detecting profiles because because of the soak period, or it was, or maybe you're soaking the CTD and it was very wavy, and so in that case, on the vessel, and so in that case, RSKtools or Ruskin will not do a great job of choosing actual profiles. So you can actually read the data as a time series and then run RSKtools, run the cast detection algorithm to find the profiles, but then you can tweak certain parameters to help you kind of to discard things that are not actually profiles. We have a function here called add station data. So if you want to append metadata to your profiles, you can do so. An example of how you would use it is here. And so if you look at one element of rsk.data, you'll see there's timestamp, and then there's the values from the channel, the sensor, and then the profile number, the direction, latitude, longitude, and all the different things. So, but this is sort of a manual process, right? We actually are calling RSK add station data and then we're inputting the coordinates and the name of the cruise and station name and so forth. Going to be mindful of the time here. We have because I'm going quite slow. We have functions to plot. So RSK plot data, if you want to plot the time series, you can do so with RSK plot data. Channel, there's temperature. In this case, you can tell it which channels to plot. If you don't specify a channel, it'll plot all of the channels. If your data is organized as profiles, we have a RSK plot profiles, which does exactly that. And again, you can specify the channels if you wish. If you don't tell it which channel, it'll plot all of them. You can specify the cast direction, the profile numbers you want to show. We even have an RSK images, which is to make these sort of heat maps or these Havmöller diagrams or whatever you wish to call them. It's called RSK images. This particular example, I believe, is from a moored profiler, probably a wirewalker. And the color maps you see are using the CMOcean color map. So if you choose to use RSK images, we highly recommend you download the CMOcean color map. Okay, and then we have a function to plot TS diagrams. And all of these functions output the line handles and the axis handles so that you can modify the line types and colors and so forth. This particular function requires the seawater toolbox, Gibbs seawater toolbox, because it needs to calculate potential temperature. So for data processors, yeah, I'm gonna blow through this pretty quick, even though I kind of went on to say this is the most important thing. But a couple weeks ago, I gave a talk on dynamic corrections for CTD. So a lot of this stuff is related to the dynamic corrections, and so I can refer you back to those presentations for sort of background information. And I do have a link to them in this talk somewhere. But for example, one thing I might do first is just smooth temperature and conductivity. And so we have an RSK smooth. It's just a running mean type of filter. You can choose a triangular window if you wish. You could use a median operation instead of a mean if you wish, but you just simply specify the length of the window you choose to use. And this is in samples, by the way. So this in this particular case, I'm doing a running mean of 5 samples. And so the output would look like the following. On the right-hand side, you can see an example of smooth data. I would then, depending on the instrument I have, and again, this is one of those cases where it depends very much on the CTD you have. And so I would refer you back to the dynamic correction talks to determine exactly what the best parameters are for this. But we do have a function called RSK align channel. And it simply takes a channel, in this case temperature, and it shifts it in time. And you can specify that time by samples or by seconds. And you can see in the graph, the blue curve is the original data, and that black dashed curve is the lagged data. And so this is helpful when you're trying to align conductivity and temperature to reduce salinity spiking. Right, so here, I'm not going to go through this in any length, but I just want to point out here that there are links to the dynamic correction webinar here for referring to information about correcting conductivity and temperature for sensor response time and lag and so forth. We do have a function, and I did mention this a couple of weeks ago, but called calculate the CT lag. And so this actually uses an algorithm written by Clark Richards, which is at DFO, to try to estimate the optimal lag between conductivity and temperature. So one may choose to use that. Often when we're at sea, the ship is heaving up and down, and that introduces variability to the descent rate to the CTD. And so in Siebert software, this is called loops. And so we have a remove loops algorithm. Okay, so what may happen is that, ideally, if you were descending, the CTD was descending at a uniform rate, you would have a nice, perhaps smooth curve. But if there's a lot of variability in the descent rate of the CTD because of waves, then that really will impact your profile heavily. So we have an algorithm that helps to find that data that was impacted by sort of variable descent rates, which is mostly a ship heave issue. And so the animation here is the following. You know, if the CTD is ascending, but if it's wavy, it sort of oscillates through the water column as it moves down. And so what our algorithm does is it says, well, hey, this data doesn't even meet the velocity threshold, the descent rate threshold. And this data, in fact, is overlapping with the previous cycle of descent. And so we're going to remove that. So the algorithm chooses these two different parts of the curve. And then in this case, it replaces those values with a not a number. So here's an example of a case where there was a lot of variability in the descent rate, and the algorithm picked out the little red dots and flagged those as being potentially bad, and then replaced them with not a number. And so that improves the data a little bit, removes some of the little spikes, especially where the gradients are strong. We have a despiking algorithm. This is sort of a median filtering algorithm. I'm not going to go through the details of it, but it could be useful in optical data, for example. Quite often, like turbidity sensors often will have spikes, and you can use despike to flag those, and then you can interpolate over them. You can replace them. Sorry, you can. Yeah, there's different algorithms to deal with the spikes. You can just not a number them. You can interpolate through them. You can replace them with the median with a filtered value. One particularly useful and powerful one is bin averaging. And so we can bin average the data by time. In this case, bin size is specified in seconds, I believe. So yeah, in seconds. And so here's an example where we're bin averaging data in time, the time series. But you can also, of course, bin average by depth or seat pressure or pressure or whatever you wish to use. In fact, you can use any channel, but you know, so far I've only found uses with depth and pressure and time. The algorithm is relatively complicated in the sense that, well, let me put it this way. Most people will just choose to bin the depth to uniform intervals, but we actually also have the choice here of binning by regimes. In other words, you can change the bin width as a function of pressure or depth. Most of the post-processing functions, if not all, in fact, have an option to visualize the output. And so if you just add this line called visualize one, if you add this parameter value pair called visualize and then a number here, which is the profile which you wish to look at, it'll actually, the RSKtools function, whether it's bin averaging or smoothing or aligning or anything, will actually output, will make a graph showing you the original data, the process data, and that data which was flagged. So for example, in despiking, the little red circles on the graph are the flag data. And so that's really, really helpful. And we use this, I think this exists for all of our post-processing functions. So you don't have to draw the graphs yourself because again, the RSK structure is a little bit clunky at times. And so we've made it easy so you don't ever have to really go rooting around the RSK structure to plot data. And so there's a visualization of bin averaging. We have a series of functions that derive new variables, mostly using the TOS10 Gib Seawater MATLAB toolbox. And so we can derive sea pressure, profiling velocity, sound speed, specific conductivity. And then specific TOS10 variables are depth. Well, it's using the TOS10 function, but not a TOS10 algorithm for depth. Anyhow, practical absolute salinity, potential temperature, density, buoyancy, frequency, and a few others. And when you use this, it just adds a new channel into the data. Okay, and so you can see that on the right-hand side. There's a couple more advanced functions that I didn't want to get into today, but there's a correct tau algorithm, which is a sharpening algorithm. So if you have a slow response sensor like an 8-second sort of optode, you can reconstruct the high frequency part of that with RSKcreate tau. It uses a particular algorithm by Fosdar. I'm going to skip through this pretty quick, but here's a graph illustrating the effect or the output of that function and how it recovers some of the high frequency energy. We have a function that applies the Luke and Piccolo algorithm to correct for thermal inertia of the conductivity cell. Okay, and so the algorithm's here. This is all in the paper that's listed below. And finally, we get to the exporters. So you can export data as a CSV file. And here's an example of what the CSV file might look like. And you can choose the channels you want to write to it. You can add comments. You can change where, you can choose the directory to which the file is written. There's also a whole section in the header of the file that's reserved for station information. So if you added station with add station metadata, it would show up here. If you use ODV, we can write ODV files or files that are compatible with ODV. You can actually take an RSK file, read it into with RSKtools, modify it, and then output another RSK file. So you could actually open the file with Ruskin again. So you could do a bunch of operations to the data, drive new channels, filter it, all this kind of stuff, and then write an RSK file, then reopen it with Ruskin again if you wish to do so. And then we have a function called RSKcreate. And so the point of this one actually is you can take data from any instrument. And what RSKcreate does is it creates a structure with that data that has the format that RSKtools recognizes. So if you have any other CTD from any manufacturer, floats, gliders, legacy RBR instruments that produce those hex files, if you can get that data into MATLAB, you can use RSKcreate to actually create an RSK structure and then use any kind of RSKtools function to operate on it. So that's super helpful. We use this one quite a bit, especially with glider data. Yeah, and so that's it by way of slides. It went a little bit long, I'm sorry. As Eric pointed out, before we get to questions, there's a couple of webinars coming up, CTD and sensor calibrations, and then wave measurements. And so that was rather abrupt ending, but I needed to rush through it, so we had time for questions. So thank you.
Yeah, Mark, thank you very much.
Yeah, were there questions?
Yeah, we answered some of the questions along the way, but we've got a couple questions that I think people that are watching the video will want to hear, and some that were a little bit longer discussion that we thought would be better if you answered directly. First, at the beginning, there were some questions about the MATLAB toolbox. First, do you have to have real MATLAB installed? Is it an executable that you can run without MATLAB? And I think the answer is that you need to have the full MATLAB, proper MATLAB software running on the computer. It's not an executable. Is that correct?
Yeah.
Okay. The next question was about toolboxes. Do you need any special signal processing toolboxes or just the standard MATLAB and then access to free toolboxes that are online?
Yeah, no, in fact, yeah, we wrote this so you do not need any paid toolbox. In fact, strictly speaking, you don't need any extra toolboxes at all, but we highly recommend the TIOS-10 Seawater library, which is free, and the CM Ocean color maps, which is also free. If you like to use our function that draws the sort of 2D time depth type of heat maps.
Okay.
So you do not need signal processing, nor you need statistics. You don't need image processing, any of these things.
Okay, excellent. Stephen had a question which I thought more people would want to hear the answer to and might be more for discussion. He asked, what window length would you suggest for RSKtools, for RSK Smooth?
Oh, I would put it depends a little bit. Yeah, I would roughly use, I go on the order of a window length. Okay, so the window length isn't the number of points, but I picked the number of points so that you get to a window length that's less than a second. So maybe for a 6 Hertz logger, I use maybe 5 points, maybe even 3 in that case. Yeah, there's really, and that will ensure, I think without a doubt, that you're basically matching the time constants of conductivity and temperature.
Okay. And I think that Eric is actually asking a question along the same lines. Yep, which is, I think you can maybe see in the chat area, but he asks, how well does a function that automatically tries to find the time lag work versus just trial and error? And I think that it's just a systemized trial and error, just tries all of them and finds the best solution.
Yeah, so that algorithm is okay. So one of the so that's a good question. It works pretty well, but you have to be a little careful because first of all the data on which you run that algorithm needs to be fairly clean in that it cannot have any contamination by the surface or any other sort of thing. So, and also in that algorithm, you can actually choose parts of the profile to look at. And I would choose one that, ideally would have a couple of strong temperature gradients. Yeah, that would be it. I would choose it as part of yeah, that's right. Yeah, I wouldn't choose the whole profile. Just because you run the risk of variations in profiling rate will come in and cause spikes in the data sometimes, which are not caused by sensor alignment. So experiment with different parts of the profile. You can even set up a little loop where you can actually just choose little 10-meter sections of the profile and run an algorithm for little 10-meter chunks, and then see what the results are.
In association with that, he asks if the fit is a cross-correlation approach to find the best lag. I don't think it is. I think it's looking for the least number of outliers or something like that. Is that correct?
Yeah, that's right. It is. It's just computing salinity for a whole range of lags and finding basically the smoothest salinity. So I've often wondered if that's effectively doing the same thing as a cross correlation, but I don't know the answer to that. I know. I guess okay. So what I do in the end is I always run the calculate function, and I look at the result and I compare it with what I find, basically by eye. And I don't ever expect to find lags between conductivity. So on a profiling instrument with a fast thermistor, I don't ever expect to find lags that are greater than a few samples. So a few hundred milliseconds at the most, or 0.2 of a second lag. You really don't get lags much larger than that. So they always should be, if you find an optimal lag, it should be just a few samples. And in the case of the combined CT cell, which has a thermistor right on the conductivity cell, there's really should be no lag at all. Maybe a sample at the most, depending on the sampling rate, but less than 100 milliseconds.
Okay, good. We're getting lots of good questions in here. I'm actually struggling to keep up. Felipe, you asked about what's going on in version 3.4.1 versus 3.00. I'm not going to put Mark on the spot for answering that directly. I will say that it's documented. So if you download it, you might be able to see what the benefits are for you.
I think on the documentation site, you can actually look at, well, you can look at the release notes. That will tell you. Yeah, okay. That's the easiest one. On the documentation site or the Bitbucket site will have the release notes for every version.
Okay. Now I'm going down. Samantha asks, can you see her question? Because it's longish.
Let me find it.
It was from time 144. Well, that's when everyone else is.
Oh yes, so that's right. So when you derive a channel, it'll overwrite an existing channel with the same name. So if you do not wish to do that, we do have a function that you can add a channel sort of manually. And if you give it a different name, then it of course will not overwrite the existing one. But so anyways, yes, the default for all of these things is to overwrite. If I just say RSK derive salinity, it will overwrite any existing salinity channel. If there's no salinity channel, it will add it.
Super. Now we have Sarah's question, which is just below that, asking about Latin long.
Yeah, so the add station data, I guess the idea there is can you add lats and logs based on timestamps? Oh, I see. You could add a channel called latitude and longitude. That could work. Well, anyways, RSK add station data really is designed just to well, okay. There's no reason why you can't manually just say rsk.data.latitude equals an array. I'm not so sure that, and that wouldn't really affect much down the line, but there are functions that will look for position. So if you are computing absolute salinity and you have a latitude and longitude, we're going to use that latitude and longitude to compute absolute salinity, for example, because that depends on where you are in the ocean. That's just the TOS10 toolbox. So there are cases when having a vector of latitude and longitudes will break things down the line. But anyways, add station data was not really designed to handle a vector of latitude and longitudes. It could. I mean, sorry, you can do that manually, but add station data.
You can force it in there.
Yeah, that's right.
The last question I think we have now is, it's going to be close to your heart and things you've done recently, and it's a good one. Do alpha and beta constants for RSK correct TM for the concerto, are they the same as for the Argo and Legato? So it'd be for normal concerto CTD profiling.
Well, okay, so the conductivity cell on an Argo float is the same as the conductivity cell on a concerto. So they're going to be about the same. And the reason I say about is because there's a profiling rate dependence here, and this is still something we're working on. So if you happen to be profiling slowly with a concerto,
10 centimeters per second on that order.
Yeah, sure. You can use the values that we have derived or computed for an Argo float, an rbr-Argo float. We're still working on quantifying those values over sort of higher profiling rates. We have some ideas for what they should be, so I encourage you to get in touch with us offline, and we can talk more about it.
Okay, last question from Sarah, which is great, and then we'll actually open it up for anyone else that wants to jump in verbally. It's been wonderful to have all these great questions and to have so many people sticking around for this. So Sarah asks, can you view raw data with the toolbox, such as voltages for pH?
No.
There you go.
No.
Okay, because that's
I was asked this question at Ocean Sciences. Sorry, Sarah, was that you I was speaking with? And I think it was about pH. Yeah.
Yes, that was me.
I actually recall sort of stumbling on this. So there's two different ways you can do it. You can either, if you find the calibration equation, you can apply the coefficients and solve for the voltage. Or I recall Greg, actually we talked to Greg Johnson about it a little bit, and he said, well, one thing you can do is just zero all the coefficients, calibration coefficients in Ruskin, and then recompute the data, and then you'll effectively have a voltage ratio. Yeah.
Okay, Sarah, let us know how that works.
RSKtools doesn't do that. Yeah, you could make a function that does it. We don't have one right now.
Okay, so I'm going to encourage you now to stop sharing your screen, and then we can open this up for sort of just video and voice discussions as well. So I'm going to stop the recording, but thanks everyone for joining, and thanks Mark, and we're going to stick around to answer other questions.